So our next speaker is going to address isolation of islet cells. His name is Dr. Balamurugan Appakalai. Dr. Appakalai is Associate Professor at the University of Louisville in Kentucky, and he's the Director of the Center for Cellular Transplantation. He has done over 1,000 islet cell isolations, another 1,000, pancreas islet cell isolation, and a whole lot of stuff. In the country right now, he's one of the best who is able to isolate the cells at a very, very high quality. So we are very lucky to have him to participate in this conference, and please join me in welcoming him to the podium.
Good morning, everybody. As an islet lab director, I would like to share with you how I process human pancreas to isolate the human islet cells for both auto-transplantation as well as allo-transplantation for type 1 diabetic patients. So my surgeon remove the pancreas in the hospital. I take the pancreas to my clean room facility, which is registered under FDA. It's a dedicated clean room GMP facility, good manufacturing facility. We process the pancreas. It takes 4 to 5 hours time with the 4 to 5 members team and return the islet cells back to the patient. So isolating large quantities of high quality islets from every processed pancreas is absolutely necessary for a successful islet auto-transplantation program, because achieving long-term insulin independence after islet auto-transplantation primarily depending upon how many islets we transplant. So many published studies reported that the strong independent risk factor for islet graft failure was low islet yield. So my goal is always try to achieve maximum number of islet cells from every processed pancreas. Extracting islet cells from chronic pancreatitis pancreas is somewhat a specialized technique when compared to isolating islet cells from brain-dead donor pancreas, which we do for our islet allo-transplantation to type 1 diabetic patients. Because of the structural changes, it's difficult to isolate islet cells from chronic pancreatitis pancreas. If you compare the gross morphology of brain-dead donor pancreas with chronic pancreatitis pancreas, you could appreciate the difference. It is difficult to isolate islets from these ones. Hence, islet yield remains a problem in islet auto-transplantation. As you see here, isolating islet cells from chronic pancreatitis pancreas poses multiple challenges: alteration in ductal structure, calcification in ducts, and accumulation of fibrous layers in the pancreatic parenchyma can significantly hinder the ability to inject tissue dissociation enzyme. If I cannot inject the tissue dissociation enzyme into the pancreas, I cannot digest the pancreas to release islet cells. If you compare the gross morphology of brain-dead donor pancreas, the procedure is somewhat very straightforward. Before I go into the detail, the basic method of islet isolation is intraductal injection of enzyme collagenase to digest the pancreas in Riccardi chamber to release the islet cells, followed by purification using density gradients in COB299 cell processor. These are the purified islet cells. After purification process, basically the intact pancreas will become cell clusters after digesting with the enzyme collagenase and protease. So we use Riccardi chamber to digest the pancreas. As you see here, these are the isolated islet cells stained with the dithizone, and these are exocrine acinar cells. As you know, more than 95% of cells in pancreas are exocrine cells. So I need to purify these islet cells after this digestion process. The entire islet isolation process is well standardized, utilizing thousands of brain-dead donor research pancreases. These are the common steps we use to digest chronic brain-dead donor pancreas for our islet allo-transplantation. Commonly, we use like 1 vial of collagenase and protease for intraductal injection, and we use pressure-controlled pump to inject the enzyme into the pancreatic duct, and we use the duration of 12 to 15 minutes. That's our standard enzyme injection duration. There is no parenchymal injection or no enzyme recirculation in the case of brain-dead donor pancreas. Most of the laboratories follow this islet isolation procedure, but these procedures are not really effective in maximizing islet yield from chronic pancreatitis pancreas. So this is a fundamental problem. So we need to follow, different new method for our chronic pancreatitis cases. Then the other problem is there is no clear cutoff for islet isolation success in the case of chronic pancreatitis pancreas for our islet allo-transplantation. For example, in the case of clinical allo-transplant, for our allo-transplantation, there is a clear definition of islet isolation success. For example, if we get less than 350,000 islet equivalents, which won't be sufficient to transplant 5,000 islet cells per kilogram body weight, that is the product release criteria. So then I can clearly say, if I don't achieve this number, it's a failed isolation. When I process pancreas for my research isolation, if I get less than 200,000 islets, it is considered as a failed isolation. But in the case of chronic pancreatitis, whatever the number we isolate, we infuse into the patient. So we don't know exactly, what is our cutoff. How do we really know, what we are achieving is the maximum number of islets, from those resected pancreas. So in my view, the islet isolation success for chronic pancreatitis pancreas for auto transplant should be the undigested tissue mass. So that is, if we have less than 10% undigested tissue mass, that should be the real cutoff for auto transplant. So during human islet isolation for auto transplants or allo transplants, we face entirely two different discrete problems. For example, in the case of islet allo transplantation, many times we notice low number of islets after digesting the pancreas. For example, if the islet yield is less than 300,000, we know this is not going to be sufficient for our transplant. So, but in many times, we see large number of islets after digesting the pancreas, and because of a purification process, we lose a lot of islet cells, especially if the islets are embedded. So this is a common problem in the case of islet allo transplantation. In the case of auto transplantation, digesting the pancreas itself is a real problem because of the fibrosis nature. Sometimes we get good number of islet cells, but we end up large tissue mass because mostly the purification process is not commonly done in chronic pancreatitis pancreases. So sometimes we end up really large tissue volume. It's very difficult to infuse because we don't want to increase the portal pressure. So these are the two common problems we commonly see in allo cases or auto cases. This data from University of Minnesota shows varying islet yield of less than 15,000 islet equivalent to over 1 million islet cells. From 476 cases, these isolations are somewhat done in the recent periods from 2007 to 2014. So whenever we achieve large number of islet cells or above 200,000, it is not a major concern. So whenever we get low number of islets, then especially we see low number of islet cells, especially from severely fibrotic pancreas, then it's a real concern how to really maximize islet yield from these cases. So there could be only two possible reasons. Either the number of islet cells in the given pancreas, in the resected pancreas is really low, or really the technical difficulty to recover the islet cells. So when we analyzed histopathological analysis of various severely fibrotic pancreas, shows varying amount of fibrosis plus a different islet architecture. But in many cases, we see large number of islets. We could see like a heterotropic, hypertrophic nature of the islet cells even in severely fibrotic cases. For example, when the islet yield from minimal change chronic pancreatitis is comparable. It was equivalent to brain dead donor pancreas, which we use for our islet allo transplantation. Even the gross morphology of minimal change chronic pancreatitis is similar to brain dead donor pancreas. The degree of fibrosis and the degree of acinar atrophy generally affect the islet yield. We get low number of islets in severely fibrotic pancreas when compared to minimal and moderate cases. So So we analyzed many severely fibrotic pancreatic specimens, and then we use islet area fraction measurement to see, are we really seeing low number of islets? In many cases, as you see here, there are plenty of islets in this pancreas. Although this pancreas is severely fibrotic, it's really difficult to digest the pancreas to release these islets. So that's why the technical difficulty also plays a major role in chronic pancreatitis cases. So in my opinion, the key approaches to maximize islet yield is to minimize the undigestion of chronic pancreatitis pancreas and the effective enzyme delivery and dosing the enzyme according to the severity of fibrosis, and the purification method to reduce the tissue volume instead of trying to purify the islets. We don't need purified islets in the case of chronic pancreatitis cases. So we want to try to get reduced volume of tissue. So with this approach, it's easy to gain high number of islet cells. For the technical difficulties, because many pancreas comes with either dilated duct, or many times we don't even see the duct because there is a large number of calcification in those ducts. So we have to make sure to really deliver the enzyme through the duct or through the parenchymal injection. Depending upon the fibrosis nature, we have to dose the enzyme collagenase and protease to digest those fibers. And we have to select the collagenase and protease, which they have the capability to binding to this extracellular matrix for the digestion process. For example, so our main goal is to minimize the undigestion of these chronic pancreatitis pancreas. For example, this is a classical example from a brain-dead donor pancreas. You could see minimal pancreas with large ductal cells. Again, this is another classical example from chronic pancreatitis pancreas. But this is a bad example from chronic pancreatitis pancreas in which we couldn't really digest large number of tissue. So when we did histology, we could see a lot of islet cells in this process. So our goal for when we process pancreas for chronic pancreatitis, it is mainly how to really minimize this undigested tissue. For example, this is the standard approach. These are the modified approach we commonly follow for our auto transplants. So instead of using just one vial of collagenase and protease, which we commonly use for our brain-dead donors, so we dose the enzyme. We want to make sure we have more than 26 Wunsch unit per gram pancreas of collagenase, and we use hand syringe injection so that you can really feel the pressure. When you try to inject the enzyme, whether you see whether there is a infusion of enzyme into the pancreatic duct or not. Then we inject the enzyme instead of 12 to 15 minutes. We prolong the enzyme distension. By this method, you are not harming the pancreas. Basically, you are initiating the digestion during this distension process. And mainly, we need a parenchymal injection and the enzyme recirculation approach. For these pancreas, we don't need, but we need to really bring this technique for our auto transplantation process. The extracellular matrix composition is very different in chronic pancreatitis pancreas compared to normal pancreas. So we have to make sure our enzyme is capable of digesting these fibers. For example, in brain-dead donor pancreas, the collagen matrix type 1, 4, 5, and 6 are uniformly expressed. But in the case of chronic pancreatitis, these fibers are expressed in very high levels. Sometimes we see more than 1,000-fold increase in collagen and basement membrane proteins. The other example is especially the type 6 collagen and laminin levels are high in chronic pancreatitis pancreas when compared to brain-dead donors. So we have to make sure our collagenase and protease are digesting these fibers to release islet cells. These are the 3 commercially available collagenase enzymes. These are the commercially available ones. So each company, they supply collagenase and protease in different combination. For example, the company Roche, they supply collagenase in combination with thermolysin. The Serva enzyme company, they supply collagenase and Clostridium histolyticum neutral protease instead of thermolysin. And then the company Vitasite, they supply collagenase and BP protease. So among the labs, generally, it's very difficult to really pick which protease. Collagenase is common in all three companies, but what is the best protease for chronic pancreatitis pancreas? Because these enzymes are commonly designed for isolating islet cells from brain-dead donor pancreas for allo-transplantation. So we did extensive HPLC analysis, biochemical properties of these collagenase and proteases, and understanding the binding properties of these enzymes. In 2012, we developed a new enzyme mixture combination. Using this enzyme, we could digest more than 90% of the pancreas when compared to other enzyme combinations. And in recent times, we did more than 9 design of experiments utilizing more than 100 human research pancreases to test different ratios, combinations, and doses, extreme doses of collagenase and protease to really decide which one is really suitable for mild pancreas, moderate pancreas, and severely fibrotic pancreas. So ultimately, this is kind of our recommendation. This gives more details. Basically, we want to have more than 26 Wunsch unit. If lab is using neutral protease or dispase or thermolysin, this is kind of our recommendation. As enzyme distension is the critical step in the entire islet isolation process, we want to make sure we deliver the enzyme properly, either using pump in the case of minimal change chronic pancreatitis like this, or using a hand syringe injection to deliver the enzyme throughout the pancreas. In some cases like this, when we see heterogeneous distribution of enzyme, for example, tail portion and duodenal portion received a large amount of enzyme, but here there may be a calcification in this region. So we may have to cut the pancreas, recannulate, and inject the enzyme to reach all parenchymal tissue. In some cases, if the fibrosis is so severe, as you see here, the parenchymal tissue is replaced with white fibrous tissue. So we directly inject the enzyme throughout the pancreas. So otherwise, you cannot really digest these type of pancreases. And we cut the pancreases into numerous pieces so that those pancreases get more enzyme exposure. These are the small techniques we follow to digest the pancreas. And even after selecting the best enzyme combination, best enzyme delivery method, sometimes during the digestion process, we don't see digestion at all in Ricardi chamber. So we wait, usually the digestion time is 15 to 20 minutes. If digestion prolongs more than 30 minutes, we do the enzyme recirculation approach. Basically, with this approach, we open up the chamber, we open up the circuit, collect the enzymes along with the cells, quickly spin the compound, and collect the tissue pellet, and add the enzyme back to the circuit. With this approach, it helps to digest the undigested portion of the pancreas. So this recirculation approach is really essential for chronic pancreatitis pancreas, especially if the digestion process prolongs more than 30 minutes. When we isolate islet cells from pediatric cases, we do a lot of pediatric islet isolations. We see this type of mantled islets. Islet cells are embedded inside the exocrine compartment. Although the exocrine compartment provides some kind of mechanical support to islet cells, but it's difficult to purify the islet cells. All these islet cells will sediment in the core bag. It's very difficult to really recover these islet cells. Moreover, so this is the normal islets, free from exocrine cells. It's easy to separate. So when islets are like this, it's extremely difficult to separate. Moreover, the islet tissue mass from pediatric cases is very high. From single gram pancreas, we get almost 0.5 cc pancreatic tissue when compared to older donor, in which commonly we get 0.3 cc. So we developed the young donor islet isolation protocol utilizing many brain-dead donor pancreas from 5 years old, 2 years old, 17 years old, even 6 months old human donor pancreas to isolate mantle-free islets. So in the fundamental of this procedure is reduce the mechanical digestion during Ricardi chamber and enhance the collagenase digestion during the enzyme distension step. We go for a prolonged enzyme distension. Basically, we initiate the digestion before it goes into the Riccardi chamber. Sometimes we may have to use 2 screens, in the Riccardi chamber to get mantle-free islets. Recently, we kind of really, we modified the technique and we consistently obtain mantle-free islet cells. In this case, from a young donors, we extensively characterized extracellular matrix components, including various collagen and basement membrane. Based on this, we developed a trisected pancreas model to test different enzyme combinations to identify which combination gives better islet morphology in pediatric cases. For example, in this case, when we have to have a low amount of collagenase and increased amount of protease in order to digest the basement membrane and cleave those exocrine cells, this approach really helps to consistently get mantle-free islets. This graph shows islet yield from different age groups. Although the pancreas is generally small in pediatric cases, but we get higher number of islet cells per gram of pancreas from these cases using the young donor islet isolation protocol. Now I quickly switch the topic to purification step. Recovering these islet cells from this exocrine compartment is extremely difficult, especially if the islets are embedded like that. So we need to eliminate these exocrine cells and purify these islet cells. Generally, purification process leads to loss of islet cells. That's why many laboratories, those who are doing islet allo-transplantation, they avoid purification step. Many published studies reported that the average recovery using various different density gradient is only 65 to 70%. So generally, almost 30% islet cell loss commonly occurs during the purification process. We developed this analytical test gradient system to understand the exocrine cell density of these chronic pancreatitis cases. So using this simple test tube method, we could measure the exocrine acinar cell density before we really run actual co-purification. This simple tube method clearly provides information about the exocrine cell density as well as islet cell density. For example, surprisingly, we observed that there is a statistically significant difference in exocrine cell density in the case of allograft as well as autograft. So brain-dead donor pancreas, generally it comes from a brain-dead donor with long cold ischemia, and chronic pancreatitis pancreas, it's from a living donor with short cold ischemia. So if we use generally the gradient materials which we commonly use is designed for our allograft. So if we use this approach, naturally we lose a lot of islet cells. For example, this is the protocol from our clinical islet transplantation consortium protocol. According to this protocol, we have to use 1.10 as a high density and 1.06 as a low density. If we use this densities, we lose a lot of islet cells. Basically, because the exocrine cell density is heavier, we tend to really sediment a lot of islets in this process. So in order to avoid this, so we use a high density purification process in which we use a high density for the bottom. With this procedure, it pushes the exocrine cells to the top layers. So we collect 1 to 12 layers in order to collect the islet cells. So in this procedure, what happens, the islet purity is not really great, but at the same time, we could eliminate a lot of exocrine cells which are sedimenting in the bottom. In this procedure, we also sediment a lot of islet cells with the exocrine cells. For example, this data shows we could reduce the tissue volume of 30 cc to 11 cc with the recovery of 87% using this heavy density approach. So this approach is definitely necessary because in the case of islet allo-transplantation, our goal is to really purify the islets. From 100 gram pancreas, ultimately we may get 2 grams, basically 2 cc of tissue in islet auto-transplantation cases from 100 gram pancreas. Even if we get 15 cc, even up to 20 cc, it is easy to recover maximum number of islets and the infusion process won't be very difficult. So in summary, so this intraductal enzyme injection for brain-dead donor pancreas, that step will be supplemented with parenchymal enzyme destruction, because both procedures should be followed in the case of chronic pancreatitis. And the enzyme injection duration is strictly 12 to 15 minutes in the case of brain-dead donor pancreas. But in chronic pancreatitis pancreas, we should really increase this injection duration in order to initiate the digestion before it goes into the chamber, Riccardi chamber. And the enzyme dose-wise, less than 20 Wunsch unit per gram of collagenase would be sufficient for our for brain-dead donor pancreas. But in this case, we need a minimum of greater than 26 Wunsch unit per gram pancreas. And the enzyme recirculation approach is definitely necessary. So our focus should be mainly on enzyme, selecting the right enzyme and the enzyme dose and the enzyme delivery approach, plus this recirculation process and the purification with the aim of reducing the tissue volume, and adding cryoprotective compound during islet isolation process, because we use more than 10 different solutions. The islets, the pancreas is exposed to all kind of stress during the process. We expose them to enzymes, we expose them to cold condition, 37 degree, and spinning those cells. So adding this cryoprotective compound, we can really improve, not only improve the islet yield, we can also improve the islet quality. With this, I stop. Thank you.
Thank you, Dr. Appakalai.